So in this video, we're going to take a look at heat capacity, and it comes in two flavors. C sub P, we can write that a little more neatly, with P as a subscript, where we look at heat capacity at constant pressure and then constant volume. So let's take a look first at the conceptual idea. If we have, let's say, a crystal of quartz, let's see if I can draw something that is kind of quasi-hexagonal. So here's a piece of quartz. And let's say we have 10 grams of it. So 10 grams of quartz. And let's draw a little cube of galena. So that's lead sulfide. And let's say we also have 10 grams of that. And let's say you put them on the stove. That's not a highly controlled experiment, but pretend this is some kind of flame. And we set the flame so that it's putting out the same amount of power to both of these materials, the quartz and the galena. Well, if we let them sit for the same amount of time, they will not heat up the same amount. The quartz will actually see a greater temperature increase than will the galena. And the reason why is that quartz has a lower heat capacity. So if we look at the heat capacity for quartz, it's about 44.5 joules per mole dot Kelvin, and then for galena, it's about 49.5 joules per mole dot Kelvin. So what does this mean? That means that for a given increase in temperature, here noted as kelvins, I have to add 49 joules, 49.5 joules of energy for lead sulfide. Whereas for the same temperature increase in Kelvin, if I have 1 mole of stuff, or in this case I don't have 1 mole, it's 10 grams, but on a per molar basis, I only need to add 44.5 joules for the case of quartz. So I've got to add more heat here to see the same temperature increase. So let's take a look at the theory. So this comes from the idea that any change in heat should be proportional to some change in temperature. And if we want to make these two things equal, we can add a proportionality constant, and we'll call it C. So we would say that C is what makes these two things, that should be an equals sign. So a change in Q is equal to C delta T, or using a calculus, dQ is equal to C dt. So we can now define C as, and it's really defined, it's not a derived quantity, it is equal to the change in heat divided by the change in temperature that results from that change in heat. But there are a couple of ways of deriving that heat. So if we start out with enthalpy, in another video we talked about enthalpy, and we derived this expression where it is TdS plus VdP. So let's say we hold pressure constant. That means dP goes to 0, this term drops out, and then this thing here, that is simply equal to Q. So dH, under conditions of constant pressure, where delta P, or dP rather, are equal to 0, that means that dH is equal to dQ. It's not always equal to dQ, it's only equal under those conditions, otherwise we have this extra term. So if C is equal to dQ over dt, we can also say that if we hold pressure constant, and now we'll write the partial, it's the same thing as this. So the heat capacity at constant pressure is the enthalpy change divided by some change in temperature. And the way we would usually do this in experimental studies is we would actually have a finite change in enthalpy over a finite change in temperature. But of course, this is all being done at constant pressure. So the CP, the heat capacity under constant pressure, this is the fellow we usually use in petrology, geochemistry, and various other places in the chemical world. But sometimes you will see instead C sub V. Now this is something different. It is not the same as heat capacity. This comes from looking at the internal energy, and the internal energy of a system is TdS plus PdV. Now here we're going to use the geochemical rather than the engineering convention, but it really won't matter because we are going to consider the case not of constant pressure, but of constant volume. So delta V or dP, these are going to be equal to 0. If that is 0, this term drops out. So notice that TdS, which again is dQ, is now equal to the internal energy. So under constant pressure conditions, so dQ at constant pressure is equal to dH, but dQ at constant pressure conditions here is equal to du. So for CV, strictly, it is equal to the change in internal energy with respect to temperature. And that's effectively the change in heat. This is the change in heat at constant volume. This du term makes it look a little mysterious, but there's really nothing mysterious about it. Look at the heat change when you have some fixed container and the sides are very rigid, it cannot be deformed. And so we look at how the system absorbs heat and how the temperature changes when the whole thing does not change in size, does not expand or contract, whereas Cp is the amount of heat at constant pressure that affects some change in temperature. So in this case, here we would let the pressure surrounding this guy be constant. It can expand or contract, and then we'll let it absorb whatever heat it would like. And it can expand and contract as it would like, and then there'll be some change in temperature. So that's the difference between Cp and Cv. In another video, we'll look at how we can relate the two and do some calculations.